Okay, so it's the question in your class. It's the question in your class in chapter 10. It's the question, the problem, and I have already sent you, giving you the solution. But next time I put here, I just explain some idea again. Okay, so now we have a plan S. And it contains these 3 points. And as we say, actually in chapter 10, I will ask you at least you should know these 2 structural problems. I mean, I will give you 3 points and give you a plan passing, and in this plan it contains these 3 points. Then you should figure out the equation of this plan. This plan. And in the process, when you want to solve its equation, you should know the normal vector of S. So of course you should know what does it mean? What does the normal vector of S of the plan S? And for the straight line, for the line in 3-dimensional coordinate system, I will give you 2 points. Then you should know the line passing through these 2 points. You should know their parametric equation and the symmetric equation. So you should know what it means. Okay, so now let's see the first question. So in the first question, if we want to figure out the normal vector means that we should have 2 vectors in the plane and consider their cross product. Then for their cross product, it will be orthogonal to original vector. So it will be orthogonal to all the vectors in this plane. So first of all, you should figure out 2 vectors in the plane. Now we have the plane S. And for this plane S, we just have 3 points. So we just have 3 points. How to get 2 vectors? Actually, you could fix X or fix A or fix B or fix C. And now we fix A, so we consider these 2 vectors. We consider AB, AC. And for the vector, just consider it's the initial point, terminal point. So terminal point subtract initial point. So it's -1 subtract 1, -1 subtract 1, 3 subtract 2, 2 subtract 3, and so on. AC 3 subtract 1, -2 subtract 2, 5 subtract 3. There's -2, 1, -1. It's 2, -4, 2. This one. Actually, for some detail, you could check the solution. What I gave you. So you could check the detail. And here we consider the cross product. So the cross product is defined in this way. We have the vector I, j, k, and here we use the determinant. So I is 1, 0, 0, but the notation is 0, 1, 0, k is 0, 0, 1. So, and here we put the vector AB, so it's -2, 1, -1, 2, -4, 2, this one. Yeah, so for its property, we use determinant, its definition, or you could say its property. But here, I is so it's defined in this way, I times determinant of 1, -4, -1, 2. But here it's positive, negative, positive. So it's subtract j times this first row, second column, so it's -2, 2, -1, 2, plus k times subtract first row, the last column, so it's -2, 1, 2, -4. And the I, j, k are vectors. And so once you plug in, you will see its value. So finally, you could see the vector is this one. You could check it. So for this vector, we could denote by n. So this vector, so n is orthogonal to AB, and it's also orthogonal to AC. Then what can we say? For these 2 vectors, you could generalize the plane S. So actually n could be orthogonal to any vector in S. It means that n could be orthogonal, n is orthogonal to any vector in S. So n, we could choose this vector as a normal vector. So n is a normal vector of S. And the probably, and as we say, and actually if who I choose this one, who I choose the vector -1, 1, 3, this one. Actually we can, right? If this vector is orthogonal to any vector in S, then this vector is also orthogonal to any vector in S, because this vector is just equal to 1/2 times n. 1/2 times n. And what does it mean, this one? It means that n and any vector u, their inner product equals 0 for any u belong to S. For any vector u in S, n and u, their inner product equals 0. But now v is exactly equal to 1/2 times n. So this inner product equals 0. Once you multiply 1/2 to n, to this vector n, you also could get that it's also equals 0. So you also could get v hat is also orthogonal to S. So v hat is also a normal vector. Yeah. It means that normal vector is not unique, but it's just it's a multiple of this one. It's a multiple of this one. Non-zero multiple of this one. Non-zero multiple of this one. Yeah, so now we could figure out, we have normal vector, now we want to figure out the equation. So we have a vector, so there are two ways, as we say in the solution. There are two ways. First one is, once we have the normal vector n, and once we could fix one point, for example A or B or C. For example, fix the point A. So the point A is 1, 2, 3. And we have normal vector, so it's our normal vector. N is this one, our normal vector. But for the normal vector, we could move it in parallel, such that its initial point is A. So here is our normal vector. We could move it in parallel. They mean the same vector. And now, how to get the equation of the plane S? Here the first way is we let any point P, we denote by the point P and denote by x, y, z. And it's any vector, any point in S. Let P be any point in S. And we want to know x, y, z, its equation. It should satisfy which equation. Okay, and here, so we use the normal vector definition here. You could see that we consider the vector AP. So AP vector is the terminal is P subtract initial point A. So it's x subtract 1, y subtract 2, e subtract 3. This one. But any normal vector means that it's orthogonal. It also means that the inner product equals 0. So since they are orthogonal, it means that the inner product equals 0. So what does it mean? The vector, normal vector n is this guy, AP is this guy. So these two vectors, the inner product equals 0. So you will get -2 times x subtract 1 plus 2 times y subtract 2 plus 6 times g subtract 3 equals 0. You will get this one. Okay. And distribution, what will you get? Organize the -2x, simplify it, plus 2y, plus 6g. Then here is plus 2 subtract 4, plus 2 subtract 4 is subtract 2, subtract 18, so it's subtract 20, this one. And it's exactly our plan S. Yeah, so it's the first way to figure out the plan. But as we say, for this plane, if you check it, you will see for the coefficient x, y, z is exactly the normal vector, negative 2, 2, 6. So actually, there are second way to solve it. Second way is that for this plane, actually once we have the normal vector, we could define x by this way. It should be the form negative 2x plus 2y plus 6z plus a constant d, but we don't know the constant d, plus some constant d equals 0. The plane as it must be of the form, but we know that a, b, c, all of them in this plane. So you could plug in a or b or c, yeah. So you could plug in a or b or c. So now we plug in a, 1, 2, 3. You will get negative 2 times 1 plus 2 times 2 plus 6 times 3 plus d equals 0. But here is negative 2, 4, 18. So you could see negative 2 plus 4 is 2, 2 plus 18 is 20, 20. So d equals 20, move it to the right hand side, negative 20, negative 20. So once you plug in the function, the equation, once you plug in the equation, what's this? It's exactly this one, this equation. It's exactly this equation. So it's the second way to solve it. Yeah, it's the second way to solve it. Okay, so it's the first question. It's the question about it's the question in section. It's a question in chapter 10. And now let's see the question in section 11.1. The question in section 11.1 is actually it's not a difficult one. As we say, at least you should know the definition. If I give you a function contains 2 or 3 variables, you should know their domain. Yeah. You don't need to sketch the graph or sketch the graph of their domain. And as we say, of course, for its domain, since it's in R2 plane, it's a stay in R2 plane. So sometimes if you graph it, you will be better to understand. But I think it's fine. If you just know it's subset, the exact set, it's fine. Anyway, so now let's read this question. We want to find domain of fxy equals square root of x plus square root of 16 subtract x squared subtract y squared. G of xy equals square root of x squared subtract y squared over x squared plus y squared. This one. Okay. And for the first one, its domain, f is domain f. As we say, xy, so xy is belong to R2 space. I mean xy belong to R2 space. And the f of xy, once you plug in the value x and the value y, it's a real number. Yeah. But if it's in a real number, I mean it should make sense. So square root, once you see the square root, it should be positive. Square root, it should be positive. This one. So of course, it's of the form. But for this form, actually we could write it this way. X is greater than 0, and here we could move it to right hand side. So, and it becomes the sum of the square is less than or equal to 16. With this one. So it's equal to this one. So for this one, actually it means that if you graph its domain, it means that we have a circle and the circle here, their sum must be greater than 0. So actually we have this one. So it's a circle, and the radius is 4. 4, 0, 0, 4, 0, negative 4 here. But x should be greater than 0. So we just have the right hand side this part. So we delete this part. So we just have this part. And its domain is exactly this one. Its domain is exactly this part. This one is its domain. This is its domain. I mean this set is exactly this part. So of course you could write down in this way. That's fine. That's fine. But it means this one, and its domain in its graph is this one. Graph of domain, not graph in the function. Graph in its domain. Okay? Domain is a subset of R2. Domain is a subset of R2. Okay. And for the second question, for the second one, let's see, G. Domain G, so we still have the, x, y belong to R2, and inside function it should be positive. It's square root, so inside function should be positive. But inside function contains it's a fraction, so denominator should be non-zero. Denominator should be non-zero. So actually it's the form. But this form we could simplify it. So if you solve it just in this step, probably I will subtract 1 or 2 points. Because for this step we could simplify. Simplify, how to simplify? What does it mean? It means that just one case it doesn't hold. It's just the case xy is not equal to z. Just xy is non-zero. Both of xy are non-zero, right? Just the case. You see, it means this case. It means this case. But this one, denominator, if xy are non-zero, if both x and y are non-zero, then it should be positive. It should be positive, then we could skip it. We just have this 10. Right? We just have this 10. So for this one, we could simplify it. Just this one. X squared subtract y squared is positive, so here is x squared is greater than y squared. And xy is non-zero. Non-zero, this one. This is a null. This is a null. But if you want to know the graph, the graph, how to graph it? If you want to know the graph, it's the form. Here for this one, we could write in this way. It's x squared subtract y squared is positive, and the rewrite it is x subtract y times x plus y is greater than 0. This one. So we have two straight lines. One is x subtract y equals 0, and another one is x plus y equals 0. We have two straight lines, so you should, if you want to draw the graph of its domain. You want to draw the graph of its domain. You could graph it like this way. Yeah, so you have two straight lines, but it should satisfy this one. So it should satisfy this one. You could just plug in some number. For example, if you let x be 0, then 0 is greater than y squared. It could not happen, right? It just could happen in the case y equals 0, but xy is non-zero. And the actual xy is non-zero, so this point you should circle it. And then, you should use this one. And so in this case, it doesn't hold, right? So if x equals 0, then we don't have any value. But their product is positive. So it means that, you could just check some point to check what's the region it should have. And here, for example, let x be 1. Then y should be, then y is greater than or equal to y squared, so y is negative 1, 1. So if x equals 1, y could be negative 1 until 1. So when x equals 1, y could be y between negative 1 and 1, negative 1 and 1. So yeah, so when x equals 1, it could be during this one. So it's the region. Here is our y equals x, y equals negative x. And then it's the same. When x equals negative 1, y is between negative 1 and 1. X equals negative 1, y is between negative 1 and 1. So it's also a graph in this region. So the domain G is probably this one. It's the graph of domain G. Just check some point, then you could graph it. Just check some point, then you could graph it. Here, and I will erase it. Yeah, so that's why I say in section 11.1, at least you should know the domain of the function. I mean the set. For the graph, it's fine. You just need to know its domain. Okay. Okay, I think that's all.